Hi, everyone. So for some reason, our class today didn't record, and I'm really bummed about that. So here's just a quick recap about what happened today, and I hope you find it useful. So we are in our hypothesis testing. Instead of actually handing in homework to me today, why don't you go ahead and upload it? There are free apps that will convert your picture or JPEG if you want to take a picture of your homework. You can download the Adobe app is the one I prefer, but any app you want, there are all kinds of free ones, and it will convert that JPEG to a PDF. So you should be able to upload about 20 files if needed, so that we don't have to physically hand anything back and forth. So that's step one. Step two, as we go through homework today, whatever questions you have, we talked about chapter 73, 81, and 85. So in chapter 73, a really quick recap about everything is that the first thing you needed to know is it gave you a percent. That percent of a population should put you in proportion land. So when you're in proportion land, you're in those formulas. Remember those NPs and Qs. Proportion should have your brain go immediately to NPQ land. So based off entering, the null comes from that 9.5 or 0.095%. From that population that we're saying that's the population's general, our understanding of this depressive rate is 9.5%. So are these 7 people out of 100, right? So it's, basically 7%. Is that a significantly different proportion than the 9% in our population? And so that's the first thing you do is you set up your null and your alternative here. So that's what you want, step one. And then you want to calculate the standard error of that. And so those are your formulas. And remember, it all comes down to the relationships between the P's and Q's. And then you can use a P calculator or your own calculator to find the corresponding percentage for the Z. That corresponding percent, you can compare it directly to the alpha. And they asked that an 05 alpha high. This is Brody. He's very interested in who I'm talking to. At that 05 alpha, you can see our percentage, our p-value, our actual level of significance, thank you, Brody, is higher than 05. If it's greater, then it's not significant. It means that it's, this isn't going to happen by chance. This is just kind of regular. These aren't significantly different. It fell within it did not fall within our range of rejection. It fell outside that range, so it's not significant. And so basically that town did not have a significantly different score. It was not significantly less. That 7 was not less than the 9.5%. That proportion, although it wasn't identical, it wasn't enough different to be on an outlier to be a significant difference. So in problem number 81, for whatever reason, they wanted to know about intelligence levels of trout. So I was unaware that there were fish psychologists, but this problem says there are. So you learn something new every day. So we have 12 raw scores from these trout. Now you can calculate, if you remember, for a sample mean and a standard deviation, you can calculate the mean and standard deviation by hand. But what I went and did is I just went and did it on SPSS because I didn't feel like doing it by hand. So I went over to SPSS. Oh, I'm on a different problem now. And I'm going to do a new program. I want to do a new data set. Okay. And my variable that I'm entering, right, is trout IQ. Who knew? And there's no decimals. And so I'm going to get rid of that because I just kind of think it's annoying to have them if you don't need to. That's just me. You do what you want. And I know that this is going to be scale, right? This is an IQ that's generally considered continuous level data. So we'll put it at a scale. And it gave me those trout scores. So I had a 5, I had a 4, I had a 7, I had a 3, I had a 6, I had a 4, I had a 5, I had a 3, I had a 6. I had a, oops. Oh, I made a mistake. I need a 3 there, not a 2. And I had an 8 and I had a 5. Now, first thing I noticed is over here I'm at a 12, which it said I had 12 scores. So yay, I ended where I was supposed to. Looks like I have everything set. I do one quick glance to make sure I didn't inaccurately enter my data, because my results are only going to be as accurate as the data I entered, right? So now I'm going to go up, and I know how to do this because in descriptives, I did this on SPSS1, and I'm going to click descriptives, and I want the descriptives for that variable. I'm going to go to the option and make sure both my mean and my standard deviation are selected. And here you are. I've got a mean of 0.492, and I've got a standard deviation of 1.6. So that standard deviation of 1.6, I'm going to take that and I'm going to divide that by the number of my sample, and that's going to get me the standard error. So, right, so I've got my 4.9, I've got my 1.6. I divide that by the square root of my sample. That gives me my standard error, and it gives me my t. Well, an important thing to remember about t is that in order to find the proportion of that t, you can either use a probability calculator, or you can use the t-table in the back of your book. So when you want to calculate the exact p-value of this, you can go to use a p-value calculator. If you want to calculate the actual t, you will plug it into the formula. So we found our samples average compared to the IQ average that we think these trout have, divided by that standard error, right? So there's our standard deviation divided by our sample. So here is our t calculated. So basically, going back to our hypothesis setup, we have a directional hypothesis, and we said it was greater than. So that means we're taking all of this percentage, all of the alpha was 0.5, all of that 5% must get put in this area of the curve, in this on the right side, because we said greater. So we mark this area at 1.96, our t fell in there. So we have to look up on our critical table, what's the critical area for significance for this group with this degrees of freedom. So you can either A, have an exact p-value, the exact level of significance, and compare that to the alpha, or you can do it through your t. So first we'll do the t. We're going to go back to our table. We're going to go back to our book. So remember, you're in a student t table now. We're not in the z. We're not in the normal table. We're in the student t because we don't have our population standard deviation. It's unknown. So we have to approximate that with our sample standard deviation, which means we're in a t distribution now. So because we were told it's a one-sided, right? It's greater than. All of that 5% in our alpha is shoved to one tail. We can use the 95% column. If it was two-tailed, we'd have to partition that 2.5% out to each tail, and we'd use the 0.975. But since all 5% are in one tail, we use the 0.95 column, and our degrees of freedom are n-1. We had 12 trout, so our degrees of freedom are 11. So 1.796 is our critical area of rejection. Since that 1.9 calculated is greater, it falls within the tail, we can reject. It was greater than. We have a 5% chance that this isn't significant, that this difference isn't significant, right? So at an alpha of 0.5, though, we can also calculate an actual p-value. So what you can do is I've actually gone into and put up for you a probability calculator that I love. And so we're in a t-test. Okay, so you can go to, there's lots of different calculators here, but I've got this set up for this t-test here. So what we know is we got to do a different thing here. Well, it wasn't our t. Our calculated t was a 1.96. And our degrees of freedom, we had 12 trout, so we have 11 degrees of freedom. We have an 0.5 alpha, and it is a one-tailed. And so we're going to calculate this. And based off that, we have a p-value of 0.037. That is less than 0.5. that gives us a significant value. So if you come over here, that 0.3, right? 0.3 less than 0.5, that's alpha, that's P, it's significant. So what we can say is for these 12 trout, their average, right, they had an average of 4.9, almost 5 IQ score. That increase of their average is significantly higher than the estimated average of a 4 for the trout. But if we wanted to try it at an 0.5 or an 0.1, for example, that's the second part of it. We can just go to our probability calculator because that's faster. And we can switch this to an 0.1. And we can say, well, so at that 0.5, it's significant. But if we switch it to an 0.1, oh, look at that. It is no longer significant. And so again, we would go to, if you wanted to check that in the book, well, what does the book say for that? Sorry, it's trying to give me, oh gosh, we don't want your advertisement. No. So it's telling us now at an 0.1 level, it's not significant. So let's go to the table and see if that points out. So 0.1, we're at 99% now. And again, it's a one tail, so we use the 99, not the 99.5. Same degrees of freedom. So again, that's a 2.7. So when we go back down to here, this T critical at an 0.1, right, alpha of 0.5 is 1.96. When an alpha is of 0.1, that was what again, a 2 point something? Is that what that said? That was a 2.718. Switching that 4%, we need a 2.7. Well, we are not. That 1.96 is not beyond 2.7. So we found a significant difference at the 0.5 level, but we absolutely did not find significance at the 0.1 level. So it's harder to find significance with a lower alpha, right? You're spreading that out. You're pushing it out to be even more unlikely of a probability that this difference will occur. That increases the likelihood that you're making the correct assumption. It decreases your likelihood of a type 1 error, right? So that is number 81. Number 82, number 81. So number 85, now we're looking at engineers. And this girl became an engineer and she heard that, yo, you're gonna be working like 60 hours a week. Good luck with that. She's like, no, I don't want to. That sounds horrible. I'm gonna ask 10 of my engineering friends and we're gonna find out what we're really working here. And so she wants this to be less than. So again, that's your cue. This is a directional hypothesis. We have a less than, statement in that formula, in the problem. We have to have a directional hypothesis statement. So basically she's saying the average is noted that it's 60 or greater. That's what you're working as a new engineer. I want to see if it's 60 or I want to see if it's less than 60. I want to work less than 60 hours a week as a new engineer. So she gets 10 scores from her fellow engineers and she has to calculate, right? We need that mean and standard deviation. Well, same thing. If you don't, going back up to the standard deviation formula, if you don't want to calculate the mean and then subtract all those scores from that mean, sum that 10 times, and then divide and take the square root. If you think back to, right, exam, your last exam, there was a question on that exam, and I told you what's a really great way to organize data. And your answer should be SPSS. So we're going to go back to this data set here. And you can see I already plugged this in. So I've got the 10 scores here. They're all in those work week hours. And I'm going to click Analyze. I'm going to go to my descriptives. I'm going to go look at, right, we've got our work week, and we're going to get that in my output. Here's my output. So I have 57 hours is the average, right? This is these were back for my trout, right? That's my trout stuff. So we're going to get rid of my trout. So I've got 57 hours with a standard deviation of 7.1. Okay, so we're going to write that down. I didn't have to calculate a thing. So we're going back down to the correct problem. So now we know I'm in the T distribution because I don't have a population standard deviation. I've got a mean of 57 with a standard deviation of 7.1. So that's what those indicate. Now that I know that, I can compare that 57 to 60 in reference to the standard error. So remember, I need that 7.1 divided by 10. Okay, and that's going to give me a t, and this is a calculated t, right? This is the one I calculated in reference to my data. So I'm going to calculate that t, but now I have to know, well, I can either compare it to my t with this degrees of freedom 9 and the critical, and I can see if it's significant, or I can calculate an actual p-value and compare that to my 0.5. So again, we have two different ways we can do this. So I'm going to go to my table, and I'm going to go here, and again, we were at an 0.5 value, and it was a one directional, so I'm in that 95. I've got a degrees of freedom of 9, which means I need a 1.833 is my t critical. Okay, so I'm going to go back and I'm going to write that down. My t critical for 9 is a 1.833. Well, I calculated a 1.3. So if I do a little thing here, right, my 1.833, I'm over in the negative land because my less than sign told me to be. But remember, your table values are always going to be positive because it's symmetrical. So it'll be exactly the same on the flip side. So we're not over here because we have a directional hypothesis with a less than in that alternative. So we're on the left side because of that. So I have a 1.833 as my t critical. So it has to be beyond that for this to be significant. But I calculated a 1.3. It's not beyond that, so it's not significant. Now, if I really want to know the actual level of significance for this t, I can go to my probability calculator. I can go over here. I'm in a t-test. My t-score was not a 1.96. It was actually a 1.3. My degrees of freedom have now changed. My degrees of freedom are a 9. I'm not in an 0.1. I'm in an 0.5 is what my problem told me. I am in that one tail, and I'm going to calculate it. So for that t, my calculation is a 0.11, right? That p-value of a 0.11 is not significant. So same thing, we found two different ways to tell us that it just isn't significant. So that actually went up to a 0.11. So that's basically chapter 9. We didn't even get into chapter 10 today, but we did get back into some SPSS, some playing. Here's another trick with SPSS that I want to teach you, and this is just for fun, and we're going to really jump into this a lot more. You can see now, I might want to ask, well, let's analyze, and let's compare these means. I have one sample of this work week, and I want to compare that work week to my sample to this 60 hours. So if I know that population mean, I can plug it into that test value. And I can click OK. And look at what it's going to give me. It's going to give me my confidence interval. It's going to give me the significant level. This is a 2-tail. So I wanted it at a 1-tail, and it didn't let me. So you can see it's not significant at a 2-tail either. Even if we didn't specify a direction, it still wouldn't be significant. And it calculated your actual t for you. And the significance is the p-value, but that's at that 2-tail. So if you go back to this calculator and you click on a 2-tail, calculate it, 225, right? A little bit of rounding, but essentially you've got it. So you'll start learning a lot of different ways, hopefully, that we can put this into SPSS and work smarter, not harder, especially with large data sets. So that's essentially chapter 9. This link and recording will be up on Cougar Courses for you. If you have any questions, let me know. I hope you found this helpful and useful, and I hope you have a great day.